The pleasure of introducing the first speaker, Shuo Zhang, who is going to give us, I think, a very interesting talk on not only Sagittarius star, which I suspect a number of people are particularly interested in, but also past outbursts of Sagittarius star, which is an interesting question that's been with us way back to early papers by Rashid, as I recall, but new evidence from new star. So Shuo is finishing her degree at Columbia with Chuck Daly, working on new stars. So this talk is going to be largely about new star data. For those who haven't seen it, they'll see some very interesting results. And without further ado, let me invite Shuo to begin. I'm unfortunately not able to be here to take the questions for the talk. I have to go teach a class at 1 o'clock. So Kosh is going to take over from the last part of the talk. Shuo?
Okay. Thanks, everybody, and thanks, Josh and Jason, for inviting me to give a talk here. So today I'm going to introduce my work on my PhD thesis, which is to investigate a hard X-ray outburst from the Galactic Center supermassive black hole, Sagittarius star. To investigate the hard X-ray emission from the Sagittarius star, I mainly use the data obtained by the New Star telescope, which is the first focusing high-energy X-ray emission operating in 3 to 79 keV. And we can take advantage of New Star's large effective area and the unprecedented angular resolution beyond 10 keV. So here's just the table list of the instrument performance, some key parameters of the instrument. So before jumping to this topic, the Sagittarius star outburst, I would like to just take a few minutes to introduce the New Star Galactic Plane Survey program. And the data I'm going to talk about today is also comes from the New Star Galactic Plane Survey. So this is actually one of the level 1 science goal of New Star. And the main goal is to try to answer the questions that what are the thousands of the X-ray point sources detected by Chandra, and what is the hard X-ray extension of the Galactic Center diffuse emission. And it started short after the launch of New Star and was completed last fall. So here's this image is just to show the New Star's pointings represented by these magenta circles on top of the Chandra 2x0.8 survey. So these ones are the completed observations. And today my talk will focus on the observation centered on the supermassive black hole, Sagittarius star, the mini survey including some molecular clouds in the Sagittarius complex, and also 2 observations centered on another giant molecular cloud called Sagittarius B2. So here just to summarize the work in our group. So besides the roughly 60 point sources detected in the survey, there are also some very interesting diffuse features reviewed in the sub-Archimedes scale. So previously, our knowledge of the high-energy observation of the Galactic Center is obtained by integral, and there was some kind of a mysterious source detected in the Galactic Center. But after the New Star's launch, and this region is resolved into this image, and we know that this source is actually composed of the Sagittarius star region and many Sagittarius complex molecular clouds, and also another famous X-ray binary source. So for the diffuse emission, mainly we have investigated 3 kinds of them: the non-thermal X-ray filaments, the molecular clouds, which emits the very significant X-ray emission, and also our group made a discovery of the hard X-ray emission, a distinctive diffuse emission component within the central of few parsecs. So although I'm involved in all of these topics, my PhD thesis focused on the hard X-ray outburst from Sagittarius star. So under this topic, I studied Sagittarius star outbursts from 3 angles. The first is the current directly detectable X-ray flares from Sagittarius star, And second is to study the past X-ray outbursts, which is actually reflected by the galaxy center molecular clouds. And I will also investigate the future Sagittarius star flare behaviors after the G2 inflow. And if the time allows, I will maybe throw in an idea that I would like to explore further during my postdoc study, which is the galaxy center cosmic ray population and origin. Okay, so the first subtopic I would like to discuss is the current Sagittarius star flares. So Sagittarius A star is the closest supermassive black hole to us, and it's remarkably underluminous with a bolometric luminosity 9 orders of magnitude lower than its Eddington luminosity. But due to its proximity and the large mass of the black hole, it is by far the best target to study the accretion physics of quiescent systems. But this quiescent state is punctuated by the X-ray flares. So the image on the left shows the discovery light curve of the Sagittarius star. As you can see, this is a Sagittarius star's quiescent state, and then punctuated by a flare event. This was discovered by Chandra back in 2001. So during a X-ray flare, the Sagittarius flux can increase by a factor up to a few hundred, and the flare can last up to a few hours. And this kind of a flare phenomena are significant in only 2 wavelengths, the near-infrared and X-ray. So for near-infrared flares, due to the polarization detection, its radiation mechanism is pinned down to be synchrotron. And also, the near-infrared flares are more frequent, like 4 flares per day, also has a longer duration compared to the X-ray flares. However, for the X-ray flares, its radiation mechanism and physical processes behind this phenomena is largely unknown. So that's why it's still a very hot topic in astrophysics. So the scientific significance to study the flares is that they are believed to be produced at only a few Schwarzschild radius from the black hole, so that the flares hold the key to infer the physical properties like the electron densities and magnetic field and so on, very close to the supermassive black hole in the very strong gravity regime. So we have just discussed that the radiation mechanism are unclear. Actually, there are different theoretical models trying to explain the radiation mechanisms of Sagittarius star. So out of them, there are 2 major classes. One is the synchrotron with cooling break. So here, the image here shows especially the red data shows the flare state spectral energy distribution in the near-infrared band and the X-ray band. So the 2 images on the bottom actually shows the synchrotron emission model, especially this one is a synchrotron with cooling break. While the top 2 images actually shows 2 theoretical models of the inverse Compton scenario. One is the near-infrared electrons upscatter sub-millimeter photons, and people call it external Compton, and the other is that it's upscattered is the synchrotron, the near-infrared synchrotron emission itself, which is called the synchrotron self-Compton. So here's the external Compton. This is a synchrotron self-Compton. So as you can see, currently the 2 to 10 keV data combined with the NIR data, they cannot distinguish between these 3 scenarios. But if you look closer to the higher energy band in the X-ray regime, you can see that the synchrotron model and the inverse Compton model predicts different spectral shape in the harder X-ray band, which is actually unique to the new star. So that's why we want to observe the Sagittarius star flares using the new star band, because potentially the new star measurement, especially the measurement of its spectral shape, can distinguish between the synchrotron scenario and the inverse competence scenario. So that's the motivation. So actually, NuSTAR by far has allocated more than 1 million seconds to observe the Sagittarius star, including the flare signs. Especially, very shortly after NuSTAR's launch in July 2012, NuSTAR initiated a multi-wavelength observation campaign with Chandra and the Keck. And there are also other different multi-wavelength observation campaigns to observe the flares. So maybe many of you are familiar with this image. We extracted the image during a flare that is captured by a NuSTAR in 2012. So this is the image during the flare and before the flare and after flare. And you can see a flare is, X-ray flare is significantly captured by a NuSTAR. And here is a 3-color image of the galactic central region. So this is also the first press release image of NuSTAR. And look closer to its light curves. Here's the light curves of Sagittarius star in July 2012 and October 2012. And you can see especially the top panel shows that 3 X-ray flares are detected in a row within 1 day. And also another very bright flare was detected in October. But here, due to the low orbit of NuSTAR, there is the Earth occultation. This is absolutely not ideal for the flare detection because for this one, we only detect the very peak of the flare and the increasing part and decaying part are all missed. So that caused some problem for our analysis. But that's the best we can have. And this is just another image showing 3 kilosecond exposure during flare and before flare, which is reported in Barrier et al. 2014. And also we have some new data coming in. This is from the 2014 to 2015 a joint observation with X-Men Newton. And very interesting, we detect another 3 flares, X-ray flares in a row within 1 day. So the top panel is the NuSTAR light curve, and for comparison, here's the XMAM light curve, and you can see there's a very bright flare here, and also 2 bright flares here. It seems to suggest that the flares occurs in clusters. So here is a zoom-in light curve and the Bayesian block analysis representation of the 3 flares we detect in the most recent Sagittarius star observation. As you can see that for these 2, we only captured the rising part of the flares. But our goal is to build a database and to collect Sagittarius star flares of different duration, luminosity, and spectral shape. And we would like to answer the question that whether the flare spectral shape has any correlation with its luminosity. So to answer this, we did a joint spectral fitting for all the flares NuSTAR has obtained by far. This is ongoing work, but just to show you some preliminary results, and here for these 7 X-ray flares detected by NuSTAR, I just group into very bright flare in green, bright ones in red, and relatively faint ones in black. If we ignore the weakest flare, which has a very large error bar, it seems to have a very weak trend to showing that brighter flares have harder spectrum. But due to the very large error bars, it's too early to draw on this conclusion. And out of the 7 flares, 2 of them have distinctive, very different flare, the photon indexes. So it seems to suggest that the flares can have a range of different photon indexes. So that's the work on the Sagittarius star flares so far. And for outlook, so the multi-wavelength observations, of course, will be very important because by far there's no simultaneously near-infrared and X-ray spectra of bright flares that exists. So from the X-ray itself, it's kind of hard to distinguish between the 2 scenarios because for the flares, the statistics is not very good. So the key to distinguish between these two scenarios will be to simultaneously determine the spectral shape in both near-infrared and X-rays. Also, another motivation to monitor the Sagittarius star flares is that it's not clear that whether there's any enhanced flare activities due to the G2 inflow. We know that the G2 itself, although it's a very much anticipated event, it hasn't been observed in the X-rays. But there has been a report of a significant increase of the flare rate and the luminosities just a few months after G2 pericenter passage. So from the data up to date, maybe it could be induced by the accretion from G2, but it could be also due to another not very interesting reason, but maybe it's just due to increased monitoring frequency due to the G2 inflow event, or maybe flares just occurs in clusters. We actually are collaborating with Gabriel Ponti. We have a proposal to do follow-up observations of the Sagittarius star flares to answer this question, which will be very interesting. So that's about the Sagittarius star current X-ray flares. And the second angle I will use to study the Sagittarius star outburst is the past X-ray outburst. Although it cannot be observed directly, it is revealed by the galactic center molecular clouds which emit X-rays. So it has been well known that the molecular clouds are very bright X-ray features. They emit both the 6.4 keV iron K-alpha line and also a continuum emission extending up to like 100 keV. So the two images on the left shows the 6.4 keV line map of the galactic center, like back in 1993, obtained by ESCA. And here is the map obtained by XMAM in 2012. And the two images on the right shows the hard X-ray emission map of the galactic center, previously by Integral and nowadays by the new star. So very interestingly, these molecular clouds shows very different timing variability, both for the iron K-alpha line and the continuum emission. So what kind of physical process can explain such phenomena, that there is a timing variability in the iron K-alpha line and the continuum? So the most popular model is the X-ray reflection model, where the incoming X-rays cause the photon ionization, which give rise to the iron K-alpha line, and also the X-rays are Compton scattered inside the cloud, giving rise to the continuum emission. And in this scenario, the model predicts a variability on the timescale of 1 to 10 years. Sorry. But a competing scenario is actually the cosmic ray electron or proton bombardment, where the physical processes is the collisional ionization and then thermal Bremsströms. So for the electrons case, it predicts a similar variability on time scale of like 10 years. But for the protons, due to its longer cooling time, it predicts a timing variability of like 100 years. So now let's focus on one of the largest, the densest, and the most massive molecular cloud, SAGB2, which is also believed to be the best manifestation of an X-ray reflection nebula. And here shows the XMM Newton and the new star morphology of the iron K-alpha line. So in our most recent work, and we reported that the iron K-alpha emission, its variability of the SAGB2, the iron K-alpha time variability of the central region of SAGB2, which is actually a region with a radius of 90 arcsecond. And you can see that for the last decade, its iron K-alpha line has been decayed. However, due to the lack of statistics, in 2013, we are not sure whether its iron K-alpha line is still decreasing or has reached a constant background level. Only future observations can tell. Also very interesting, we detect another cloud feature very close to the SAGB2, which is called the G0.66. And it demonstrates very different timing variability compared to SAGB2. This can help us maybe to better constrain the past outburst of Sagittarius star. Yes. In the X-ray reflection scenario. And here is just shows the hard X-ray morphology of Sagittarius B2, and we detected also the two features very significant. Especially, we also detected two compact cores, main core and the north core in the Sagittarius B2. And so the broadband NuSTAR 3 to 79 keV spectroscopy has allowed us to, for the first time, to test the self-consistent models of the three scenarios, X-ray reflection and cosmic rays. And due to the time limit, our conclusion is that if the X-ray emission keeps decreasing, then the X-ray reflection model is preferred. While if the X-ray emission has really reached a constant background level, it will reveal the cosmic ray bombardment component, while the electron model can be ruled out based on the measurements. I will skip this. So besides Sag-B2, some other molecular cloud in the Sag-A complex has also been detected above 10 keV, including MC1 and the bridge. And we also analyzed their spectrum, and they basically required a X-ray outburst with a parallel spectrum with a photon index of 2, which is actually consistent with the requirement by the Sag-B2 cloud. However, it requires an outburst with the luminosity much lower than that required by Sag-B2. So it could reveal different outburst stages from the Sagittarius star. And it could also, since these clouds are closer to Sagittarius star and requires a dimmer, a fainter outburst, it seems to suggest that Sagittarius star could be much more active in the past. And for some outlook on this topic, in the future, so next year, Astra-H will be launched, and it could very accurately measure the Compton shoulder in the spectroscopy, which is actually a signature of the X-ray reflection. And also another telescope developed by China and Europe is the X-ray timing and polarization telescope, which will measure the X-ray polarization in the galactic center. This is also a signature of the X-ray reflection. And both measurements would hold the key to tell exactly the contribution from the X-ray reflection scenario. So my final topic is how about the future Sagittarius star flares. So this one is just the discovery of the galactic center magnetar. This is actually, we actually used the G2 TOO because we thought the brightening of the galactic center is due to G2. However, although it's not due to G2, it really led us to discover this magnetar. And as we discussed, so we are not sure whether the flares have higher rate and luminosity due to the G2 infall. Anyway, there's a 3.5 sigma detection of a higher flare luminosity and rate. So the follow-up observations will tell whether this is due to G2 or maybe just due to the flare clusters. But this is a work ongoing. So here's the summary of my talk, and also thanks to my collaborators. That's it. Thanks very much.
Thank you, Joel. Any questions?
Yeah, at the very beginning, the justification for the new star equations was the spectral energy distribution of the high energies. And is that yet pinned down enough that you can actually say anything about the models?
Right. So actually, for the 2012 flares, sorry, let me just. As we talked about, there are two flares which shows different photon indexes, and these are the July flare and the October flare. And in Berea et al. 2014, indeed, these two flares are fitted with are fitted with different models. The solid line is the synchrotron model, and the dashed line are the inverse Compton model. And if you only look at this flare, indeed, it can rule out the inverse Compton model because the rejection probability is like 65%, and it supports the synchrotron model with cooling break. However, this flare caused us some trouble because it seems it looks like there's a cutoff here, and no models can stand out. So it's still inconclusive from this. But that's also due to the lack of data, because for each flare, we only captured only part of it.
Any other questions? Sure, will be here for the rest of today. If you are interested in her work, please contact her.
Thanks again.
Now we are going to move on to the second talk today, given by Igor Chilingaryan. Dr. Chilingaryan got his PhD in astrophysics in 2006. It is a joint degree between Moscow State University and the University of Lyon in France. Igor was a postdoc at Paris Observatory and the Dwarf Observatory in France between 2006 and 2011. He joined SAO in 2011 as a staff astronomer at the telescope data. Igor studies galaxy evolution mostly from observations, but also from simulations. He is best known for his works on dwarf ellipticals, compact ellipticals, and ultra-compact dwarf galaxies. He has also been very active in the Virtual Observatory field, both on technological and scientific aspects. He has also co-supervised several graduate students. Today, Igor is going to talk to us about the evolution of early type galaxies and compact stellar systems. Thank you.
Can you hear me? Yeah. Hello, everybody. So I'm going to present some of the results that I obtained during the recent decade on the evolution of dwarf and not only dwarf early type galaxies. And those results will be mostly originating from optical observations and also a little bit of ultraviolet and near-infrared. And I will make a special tour into the virtual observatory technologies for those of you who are not familiar with this. So let's start from a very general slide. What do we know about early type galaxies? Early type galaxies are these objects with very regular morphologies that are also known as elliptical and lenticular galaxies. However, their evolution is not that simple as their structure. Traditionally, since the 70s, dwarf ellipticals were elliptical galaxies and lenticular galaxies were split into dwarfs and giants. And this is a plot showing the mean surface brightness versus absolute magnitude and versus effective radius, so the radius containing half of the light. And in 1977, John Cormandy, who's giving a colloquium this week, by the way, spotted a sequence of elliptical galaxies on this plot, effective radius versus surface brightness. And it was noted that brighter galaxies, more luminous galaxies, have lower mean surface brightness, so they're more extended. However, later it turned out that dwarf ellipticals that actually fill galaxy clusters and rich groups, they behave differently, and they become fainter in surface brightness once you go to the low luminous end. So there's been a lot of debate regarding whether there's a dichotomy in this diagram or it's just a projection effect because we chose the wrong parameter space. So those are observables. On the other hand, we know that stellar populations of those galaxies differ substantially, and giant ellipticals and lenticulars are dominated by old, relatively metal-rich stars, while dwarfs contain stars of lower metallicities and younger ages. So this particular point about younger ages suggests that they cannot be considered directly as building blocks of giants, because otherwise you would expect them to be old. Giant galaxies form through mergers and then evolve secularly, while dwarf ellipticals must experience a lot of troubles because of their life in clusters, so they can be stripped of gas from by ramp pressure, by the hot intergalactic medium in clusters that is observed in X-ray, and also the gravitational potential might not be deep enough to be able to sustain star formation feedback. So this is a way how they can evolve. There's another evolutionary agent that is often forgotten. It's tidal interactions and tidal stripping. And this is a very important thing in clusters for dwarf systems. And it can strip up to 95% of stellar mass from a giant galaxy, and then you will probably end up with something like an M32 that I will show in one of my next slides. You can also form tidal dwarfs during interactions, or create even more exotic objects called ultra-compact dwarf galaxies, which are really central remnants of dwarf ellipticals left after tidal stripping, where the mass loss can reach 99%. Signatures of past violent events are easier to spot in dwarf galaxies, so that's why I'll be concentrating on them. How do we approach this problem? Let's develop a new novel data analysis technique and then try to reanalyze existing data that are sitting in the archives, or maybe sometimes chase the authors of published papers and try to shake out the data from them, which sometimes is useful. Then we can carry out new observations and run simulations and develop models, and hopefully there will be profit. We'll understand what's going on. So I'll start with a novel data analysis technique that I developed during my PhD around 10 years ago. And this was the full spectrum fitting technique applied to studies of stellar populations. What people usually do with absorption line spectra. By the way, here you see a spectrum of a galaxy shown on the top, and its best fitting stellar population model in the middle, and the residuals in the bottom. And those are not noise. These are real absorption lines from stars in the optical domain. Traditionally, when people dealt with absorption line spectra, they extracted internal kinematics, so radial velocity and velocity dispersions, and stellar populations independently. And for stellar population, they were using very prominent features like hydrogen H-beta line, or magnesium triplet, or iron 5270. And therefore, they used only like 15% of the available information. However, if you try to fit the spectrum pixel by pixel everywhere, you use 100% of the information. And this is the idea behind this method. So we fit an observed spectrum with a grid of stellar population model and extract simultaneously internal kinematics and stellar population. By doing this, not only we avoid problems such as degeneracies between velocity dispersion and metallicity that is very easy to understand, because if you have deeper line in the model, you want to smooth it more, so to increase velocity dispersion in order to smear this model and match the spectrum. But also it increases the precision of stellar population parameters by a factor of 3 to 6 compared to classical techniques. Now let's make a little technological detour and talk about what's going on with the data flow in current astronomical landscape. I'll be talking mostly about optical things, and I'll try to describe in a few slides the data flow in current astronomy. In the 60s and 70s, people used optical photomultipliers. Let's talk about digital detectors, leaving photographic plates a little bit aside. There was one object and one background measurement, two numbers, kilobytes per night. In the 80s, first CCDs appeared. First, they were small, 16 digits per pixel, hundreds of kilobytes per image, up to tens of megabytes per night. In the 90s, CCDs grew up to 2K by 2K, so it's 8 megabytes per frame in the 16 digits. And first mosaics appeared, for instance, the CCD12K at CFHT in Hawaii. And these already are hundreds of megabytes to gigabytes per night. In 2000s, they grew even further to 4K by 4K, and large CCD mosaics such as MegaCam, that is now being operated at Magellan, and Mega Prime at CFHT appeared. There you're talking about 500 to 700 megabytes per frame, and this is the size of this CCD array compared to the hands of an engineer holding it. So we get tens of gigabytes per night. And what do we have now? We have DECAM operated at Blanca telescope in Chile that is a 570 megapixel mosaic, and it's hundreds of gigabytes per night. And not so far in the future, we'll have LSST that will produce tens of terabytes per night. So in the optical, everything is bad. How about the radio? This is LOFAR, a new generation radio telescope in the Netherlands. And 10 hours long exposure covering 3 by 3 degrees is half a petabyte of raw data. After you reduce the data set, you process it, it shrinks to only a few terabytes. So the data flow grows exponentially in time, and you cannot carry out your petabytes on a hard drive. Downloading them via internet will take you days. It takes minutes to read terabytes from a disk, but it might take you days and weeks and months to reduce and analyze them. However, during those weeks, you'll get new terabytes, and they also have to be analyzed. So data flow becomes a data avalanche. It can swallow astronomers. After all, only a minor fraction of data, like 20%, gets published, and the rest sits to rot in the archives forever. What can we do? What and who should we blame? Okay, those are two main questions in the Russian history and literature. So we have to invent new and efficient ways of manipulating and processing large volumes of data, and archives and databases must have standardized access interfaces and programmer interfaces. Also, we have to keep in mind that the number of astronomers doesn't grow exponentially despite the infamous PhD overproduction problem. Here's the front page of New Yorker from 2010 when a guy comes back from grad school and putting his diploma next to his trophies. So, virtual observatory is where we have to, the direction that was proposed. It's a realization of e-science concept in astronomy. And this is an infrastructure that is created by data archives and software tools that interoperate using a set of peer-reviewed standards. And those standards are developed by the International Virtual Observatory Alliance. It's a governing body that is a collaboration of, from many countries. And it forms a powerful virtual environment aimed at facilitating astronomical research and increasing scientific output of the data. The goal is to increase the number of papers per gigabyte of data with constant manpower, like saying simply. And the key ideas is to organize the global data flow and systematize everything that you can systematize. Routine operations have to be transparent, and creative minds, scientists, they should do research, but not endless format conversions. Okay, the tour is ended. Let's go back to science. Dwarf galaxies, what do we know about them? This is a picture of Andromeda taken with a small telescope. And there are two satellites, Messier 32 and NGC 205. And Bade in 1944 pointed out that although they have very similar luminosities, they have sizes different by a factor of 10. So if you assume that they're more or less spherical symmetric, the stellar density here will be 1,000 times the stellar density there. Later it turned out that compact ellipticals, where M32 is the prototypical object, are very rare, while dwarf ellipticals, where NGC 205 is the prototype, they fill all clusters and rich groups. I'll start with the observing part, summarizing what we've done on one slide. There were several papers that we published. We performed the first integral field spectroscopic observations of dwarf elliptical galaxies in the Virgo cluster. 3D spectroscopy, or IFU spectroscopy, is a technique that allows one to take a spectrum over a contiguous region of the sky with spatial resolution. So basically we have a field like a microlens array, and in every point we have a spectrum. So it's pretty similar to what you're dealing with in X-ray when you have an energy resolution, but here the spectral resolution might be as high as you want. So we detected embedded disks in dwarf elliptical galaxies that made them look similar to giants. We discovered young metal-rich nuclei in dwarf ellipticals. So here you have an age distribution of stellar age, and you see the blue. It's 3 billion years compared to 10 billion years in the outskirts of the same galaxy. And we later obtained the first large sample of DE spectra at intermediate spectral resolution with ESO-VLT that allowed us to map scaling relations such as the fundamental plane down to the dwarf regime for the first time. But this was not the end of the story. Then I went after the archival data, and I managed to get long slit spectra for 31 galaxies from Palomar and French Observatoire de Haute-Provence telescope. Those were available in the archive, and those were shaken out of the PI. I reanalyzed them using the technique that I described, and I was able to get stellar population profiles for all those galaxies. So what you see here is the position in arcseconds centered on a galaxy nucleus. This is radial velocity, so it looks like solid state rotation. This is velocity dispersion of stars. This is age, and you see here the age is like 7-8 billion years, and it drops to 2 in the center. And this is a metallicity showing very nice gradient. This was done for the first time for 30 galaxies, and we obtained pretty interesting results. Discovered 4 kinematically decoupled nuclei, so it's when the center of a galaxy rotates in an opposite way or in a different way to the main body, or the main body might not be rotating at all, like here, while there is some interesting thing happening in the center. We discovered numerous evolutionary decoupled cores, so young and metal-rich nuclei. And these all made those galaxies looking very similar to giants. So, the main conclusions that we draw that embedded disks suggest late-type progenitors. So, most likely those are galaxies that experienced the infall onto clusters, and then they were stripped by the hot intergalactic gas out of their internal ISM. And this can be easily checked, which we plan to do in the future, by comparing Fornix and Virgo clusters that have very different properties of the intergalactic medium, as you probably know as the X-ray community. One of them is very compact, another one is very diffuse, and the sizes are different. So we would expect DE populations to be different in the optical, in those two clusters. And also, those findings support the downsizing galaxy formation scenario. So smaller mass galaxies have more extended formation histories, and this doesn't allow us to consider them as building blocks of giants. Now let's switch the gears and go to compact elliptical galaxies, because this is the most interesting part of the talk. Those are M32-like objects, and until 2004 there were only 3 of them known: M32, a satellite of M87, Virgo A, and a satellite of its central group galaxy in NGC 5846 group. In 2004, Miske et al. Discovered 2 other Cs in Abel 1689, a well-known cluster redshift of 0.1. But those were not very well studied because they're still very faint. In 2007, we accidentally spotted one in the center of the Abel 496 cluster, and I actually realized that this was a compact elliptical when I looked at archival HST images. And this became the 7th one. No, the 6th one, actually. And after that, I thought, okay, there are 1 here, 1 there, 2 there. Why don't we try to use the Virtual Observatory and to do the first systematic search for those objects? So, and we designed a workflow that used HST data on central regions of galaxy clusters, analyzed them automatically using S-Extractor service, extracted galaxy images, measured effective radii, took those that were interesting to us, which were small and compact, then looked up in NAD and SDSS for available redshifts. And guess what? In 23 Abel clusters, we got 55 candidates. 14 of them were immediately confirmed from literature. They were just in some surveys and nobody noted that they were there. And then we observed 7 fainter galaxies with this Russian 6-meter telescope to confirm their nature. In order to show you what it looks like, I'm putting the same plot as on the first slide, on one of the first slides. So the absolute magnitude versus effective surface brightness. So it's rotated. Green and orange are dwarfs and giants, and this is a literature sample. And we filled up all this gap in the parameter space using the Virtual Observatory. We found that those galaxies were all more metal-rich than one would expect for their luminosities. And they had higher velocity dispersion, which is obvious because they're smaller. So in order to keep equilibrium, you need to have higher velocity dispersion. This is one of the HST images that we analyzed. And these are the simulation that we ran because we suspected that those were all formed by tidal stripping. And in fact, if you drop a Milky Way-sized galaxy onto M87, after only 600 million years, you're left with a small compact remnant. Here, those big gray isophotes are like 29th magnitude from square arc seconds, so they're really faint. And these were the first success. We published this paper in Science in 2009. And so, all simulations of M32 formation by tidal stripping were confirmed. We discovered quite a bunch of those objects, so they were not any more unique. And however, there was still a question: are they available only in clusters? And everything was okay. However, there was a bolt in the blue. An isolated compact elliptical was discovered in 2013 in the archive, by the way, again. All properties were very similar to known compact ellipticals in clusters, no evident host galaxy, so there is no body that can strip it. So there was a discussion whether there were dwarf galaxy mergers or something else. So we thought that we need the search without the environmental bias. And we went to wide field surveys in the Virtual Observatory. So we went to SDSS, Galax, and UKIDS. We cross-matched those 3 for the spectroscopic SDSS sample, fully corrected the photometry using K corrections and aperture corrections, whatever corrections you can imagine, obtained galaxy SEDs, and then tried to look at what we got. So this is a standard color magnitude plot that you used to see in the extragalactic studies. This is red sequence and the blue cloud. We tried to add a third dimension to it, which was the near UV color from Galax. And we got a thin surface. So, in fact, the red sequence here, this is a pretty complex plot. I'm often criticized by referees for my plots being too complicated. So, this is a 3D plot where you have near UV minus R color in magnitudes, absolute magnitude of a galaxy, and an optical color. And so the red sequence will be on the tip of this cloud. But in fact, the entire cloud is really thin. And it's a surface in a 3D space that includes 98% of all galaxies that we had in the sample. The 2% included various exotic objects, including compact ellipticals on the top. So they were out. And we decided to use this. I will not discuss much the color projection, but the thing is very thin. It's like 0.03, 0.04 magnitudes in the optical color. We decided to use them, to use this surface to locate CE candidates, and then to confirm their nature by measuring sizes and exploring their spectra. And we did this. We designed a new workflow, and we found all those objects that you see shown as dots, while the literature stuff shown as stars. And this was another science paper this year. These are all our galaxies sorted by redshift. So you see they're really tiny. These are SDSS stamp images. What was interesting is that in the area where we were complete, they constituted a fixed amount of all galaxies in the SDSS sample by percentage, like 0.5% of everything that you have in SDSS. We found more tidal tails like this, which were really rare, and those are short-living things, so this is another proof of them being tidally stripped. But more interestingly, we found 11 isolated galaxies, and we wanted to see what they were. So we found no significant difference in stellar population. This is age versus metallicity. You have plots, you have dots with the color corresponding to their absolute magnitude, while the background color corresponds to absolute magnitude of normal ellipticals. So you see those galaxies are much less luminous for the same metallicity. And isolated and non-isolated do not differ at all. So, can we still get away with a stripping scenario somehow? And apparently, yes, we can. Because we thought that those might be runaway galaxies. This is a scenario that was proposed by people doing numerical simulation. Laura Salas, who is at the ITC, I think, or she was a postdoc here. And they made modeling for three-body interactions in the local group and found that sometimes interactions with the Milky Way and another satellite can put a galaxy on a very extended orbit that is very close to the gravitational bounding. So it can, in principle, go away, but it's hard for very, very low luminosity dwarf galaxies because they have low densities and they can be tidally disrupted. However, compact ellipticals are dense, so it's easier for them to survive. And this is the classical caustic diagram where you have projected distance versus radial velocity difference, and galaxies which are close to the center of the potential, which are deep in the potential well, they're sitting in the center around the zero line, while those that are falling for the first time or that are getting ejected, they get close to those caustic lines. We did this analysis for the entire sample, and we indeed found 4 galaxies which were beyond caustic, so they were supposed to be free-floating. And this suggested us that the isolated galaxies must have been ejected by three-body encounters from their clusters and groups. And I wouldn't go into the details here. So, summarizing in compact elliptical, they are not rare anymore. They exist in all types of environments, but they prefer denser regions for obvious reasons. All CEs were tidally stripped, and isolated galaxies are normal CEs ejected from clusters and groups via three-body encounters. And now I'll talk for 1 minute more about my personal view on archives and the VO. In my research activities, data archives and VO are absolutely essential tools that I use on a daily basis. 100% of my papers deal with somehow with archival data, and 70% of them are purely based on them or present new resources. And moreover, in papers from major journals that I receive for review, I see more and more references to Virtual Observatory. And this looks like a good trend now. Archives, good, bad, and ugly. The vast majority of currently existing data archives in astronomy are pretty hard to use. Some good exceptions are spacecraft archives, like HST, Chandra, XMM, Galaxy, some ground-based things, and big surveys. User interfaces are usually badly designed, although there are some good exceptions. And virtually observatory interfaces are usually badly implemented. So there's an interface, but you cannot use it because it's not standard compliant and the data cannot be retrieved. Many archives still use very weird mechanisms for data retrieval, like Java applets or whatever, which is just awful. And the easiest way so far for me to access the data is using tools like Aladdin. So, why am I in a position to judge? Because I developed quite a bunch of archives and virtual observatory standards in the past, and software packages, and I did reference implementations for those standards. So, what I can tell you, the way forward would be for data centers to put major efforts in reducing the data properly. Raw data can used be by very few people. Integrate source catalogs if available, like HST or Chandra or XMM, with the archive. And VO interfaces should be the first priority for data centers, because even if your web form is ugly, people still can use those things with different tools, and they can use your data. And please use higher usability specialists, even those who are summer students in computer science, to design your interfaces, because this is so much better. That's what I promise. So that's all I wanted to tell you, and I'm happy to take questions. Thanks.
Any questions for Igor? Other than who should we blame? Okay, may I ask, so you're talking about compact ellipticals that are more likely to be found in dense environments?
Yep.
But this is true for all ellipticals, right? So relative to the general elliptical galaxies, are they still relatively more likely?
For the compact elliptical galaxy, you need dense environment to strip the stars out of it. While a giant elliptical can be formed, let's say in isolation, you have two spirals that would merge and you will get something early type out of it in the field. So that's the main difference. But for compact ellipticals, obviously, if you need high density of stellar systems in order to make tidal stripping, because, for instance, a galaxy has to pass closer than like 20 kiloparsecs to the center of a giant beast like M87 in order to get stripped. Mm-hmm.
Yeah. Your archive search, I mean, you have an idea, right? And you go to the archive to try to test it.
Mm-hmm.
There is another type of approach, which is kind of data mining, which is blind. You go to the data and let the data tell you what's in there. Do you use the similar type of interface or a similar approach in the two cases, or?
Okay. Yeah, here you're right. I'm trying to. It's always easier to look for something that you know when you know what you're looking for, than for something that you don't know. So for data mining stuff, I would say that the existing tools for data mining, the important thing is the visualization, multidimensional visualization, and in particular the concept of connected views, because the human's brain can actually perceive more than 3 dimensions, but you cannot do it with 2 eyes. So if you have, for instance, 2 3D plots, in different parameter spaces, for instance, one dimension is the same, two are different, so you're talking about 5 dimensions in total, then if you can isolate a region in one parameter space and see what it corresponds to in the other one, this can be very useful. And this can be already done with TopCat, for instance. Well, 3D is sort of hard to manipulate because you don't have a 3D mouse, even though some of them are called 3D. But in the 2D, you have like 3 or 4 plots, and you can easily find very interesting things using TopCat on archives. If you're going to aid us, I would invite you to attend the tutorial on Sunday in Sydney next week, because there will be my collaborator Ivan Zolotukhin will be running a tutorial on XMM data, and we'll probably try to set up a part of the demo using X-ray and optical together.
Any other questions for Igor? If not, let's thank Igor.
But I want to ask you publicly. Why is it that the virtual observatory activity is so much wavelength dependent? Isn't it true that it's very wavelength dependent? Like,
No, it's not.
it's primarily the optical part?
No. All the X-ray data are actually in the virtual observatory. You have integral, you have XMM, you have Chandra. You have for radio, it's a little bit worse. Oh, yeah. Sorry. For radio, it's
Radio, it's really bad.
It's really bad. Yes.
Okay. And